Hi and welcome. This lesson is as important as the previous one because here we will see the extra component involved in stateful processing, which is state store. And for me, having a stateful job without a state store is like having a car without roof. Of course, you can drive when the weather is sunny, but when it starts raining, your head will be obviously wet and it will not be very comfortable. And to understand why I use this metaphor, I invite you to the other slides where we will deep delve into the state store in different state stores you might have in your streaming applications. So state store has four purposes. So the first one, I think that you got it from the previous lesson, is to remember previous values, so that you can update your state and increment it in some sense. The other one is the state expiration. Of course, when you don't get an event, so for example, you might be working on session generation and your user might have some hardware issues, so his or her PC crashed and you don't get any more data. And in that case, you can generally apply two strategies. You can wait for the next activity of this user to close this session, or you can define an idleness period, and if during that period you don't get data for this user, you simply close the session. And state store is a kind of backend for that purpose too. The third purpose is the redistribution. So when your streaming job needs to scale, of course you will be able to distribute different states to the new compute. And finally, the fault tolerance, because it's the single unit that you can checkpoint. And for example, in case of a failure of your job or sample a restart, it's a kind of backup for everything you have processed so far and everything that you will need for the job after the restart. So in sample terms, it's a kind of persistence layer for stateful applications, right? And there are different types of state stores. So the first one is the local and in memory only, meaning that the state store is tied to your streaming job and it lives, it shares generally its life cycle. So if you have an application, let's say serverless application on Kubernetes, for example, and you deploy it with 4 Docker containers, when the state is stored in each container and when the container dies, the state dies too. So there is no persistence between failures. And that's one of the main drawbacks because yes, it's fast access, it's local, but if there is something bad happening, well, you will need to recompute the state or you will simply need to start from scratch for the scenario you're implementing. And among the examples, you can find dictionaries in Python or maps in Java Scala, data structures, or embedded databases like RocksDB, which is quite popular, by the way, among the state store implementations in distributed data processing frameworks like Apache Flink or Apache Spark Structured Streaming. The second state store is an in-memory local, but with fault tolerance. So here the idea is still to have this fast access to the state in continuous mode, but provide some fault tolerance mechanism that you can use in case of any failure in the state recovery scenarios. So there are different ways to write this state in fault tolerance. It can be written regularly, for example, every microbatch, every 1 minute, or more rarely. And here it's up to you to define the logic, the custom logic for that. So here it's still fast access, but there is some overhead for doing this checkpoint depending on the strategy you apply. If it's a regular one, for example, for the microbatches, of course, the execution time of each microbatch will be increased by this checkpoint writing. On the other hand, you have this guarantee that when your job needs to restart, to recover, or maybe you need to redeploy your job on a different infrastructure, well, you will be able to access the state again and recompute everything and start from some point in the past and not from the beginning and not from the now. And among the examples, there are the same examples as previously, so dictionaries, maps, RocksDB, plus object store. Typically, it's well known for that. Object store is the mechanism well known for this checkpoint and fault tolerance provisioning. Of course, it can be also a distributed file system. It's up to you and to adapt to the infrastructure you have. And the third big category is distributed. So in simple terms, we don't have any local state store here. We have just this distributed state store where we access each time we get some state data to update. And it's of course slower because there is the network overhead, and accessing the network is always slower than accessing data in memory of your nodes. It's also an external dependency you need to maintain besides your running infrastructure. And the nice thing is that it's a database, so you can allow other applications, other users to query the state store, but it also has other and a darker side that when you make your state store public, you will need to deal with everything which is related to schema evolution and stuff like that, so that other customers can follow. So generally it becomes more a data exposition layer than the internal state store of your stateful streaming job. So here you can obviously use things like key value store that by definition are fast in access, still slower than in memory, or memory store with persistence. Of course, it's also slower because it involves network traffic. And now I think that the question you're asking yourself, which one is the best one? So unfortunately, there is no single answer, but I would like to give you some hints what to choose. So the industry standard, I mean, the implementation in Apache Flink, in Apache Spark Structured Streaming, which are two leading streaming frameworks at our time, is that we have this in-memory access with optional, not optional, but with fault tolerance. So this fault tolerance can be configured. In Spark Structured Streaming, as of this saying, it's regular, so after each microbatch it writes a state. In Flink, you can configure the checkpoint duration for that operation. So it's a bit more flexible, but of course, having this irregular versus irregular checkpointing doesn't provide the same semantics in case of a recovery. And when you develop a custom application, you can use both. You can use both scenario. You can use as well the industry standard, which is for me good enough, or you can also try to work with distributed data store. Maybe if you have something like CDC that you can plug to this distributed data store, so generally you can write your state and after that have another streaming application consuming the state in real time. So this CDC stands for Change Data Capture. I covered this part in the module, I think module number 2 about data ingestion, or module number 3 about the data ingestion in real time. Anyway, I let you check the schedule, but still it's also can be a good idea. If you are not familiar, or if you and your team are not familiar with distributed data processing and you will not want to become familiar with that aspect, which is obviously fine, and it's up to you. So thanks for watching, and see you in the next lesson where we will follow our exploration of stateful processing and different stateful processing components.